two, you have pharmacokinetics and clinical pharmacokinetics, and it's an extremely math-heavy course, and that's why some of you will do fine in it and love it, because it is a fascinating topic. It's a mathematical and statistical modeling of how the body handles the drug. Cool, right? Some of you are like, oh my God, he's already lost me. I don't care about that. Anyway, but you do need to be able to get through those classes. So no more than anything else, to introduce some simple topics and show you the formulas and the types of math that you have to be able to perform to answer those questions. So certainly more important than an in-depth knowledge of some of the topics. But then again, I can't talk about the math without doing some of the topics. So I outlined some of the topics there. I think it's best just to kind of get started with this and try to set it up. A broad definition of pharmacokinetics. Now, I'll tell you now, I think my recorded lecture that I did for this is way better than what I'm going to do right now, because I took the time, I had my little notes, and I could kind of read some of those definitions in a little more description. So that I would definitely refer to the recorded lecture for some of the backgroundy stuff. But pharmacokinetics, have you guys talked about it yet? If I said ADME, do you know what ADME stands for in pharmacology? Absorption, distribution, metabolism, excretion. What the heck is LADME? And I think for this lecture it's important, and they're trying to add that on there. L stands for liberation, all right? Let me ask you this. So let's use an example. Let's just say you've already developed a headache from listening to me and need to take an ibuprofen, okay? Ibuprofen is available, it's a powdered substance. Do you have to dissolve it in liquid to swallow it, or does ibuprofen come as a tablet? Isn't it kind of, why do things come as tablets? Because you can just pick them up and swallow them, right? You can get all the powder you need and it's gone. It's really convenient, all right? Versus when we used to have to lose powder packets and dissolve it in water and drink it, and it tasted really nasty, right? It's real easy to use a tablet. But for the drug to get out of the tablet, what does it have to do when it gets into your stomach? It has to dissolve. It has to essentially separate itself. The powder has to be released from what's inside the tablet, and then that powder has to dissolve in the gastric intestine fluids, and the acid will dissolve the tablet, and then the water in there with the drug powder can dissolve in that, and then it's finally able for the A, which is what? Absorption. So L really stands for liberation, meaning if whatever dosage form you give, the drug has to get out of the dosage form before it can even be absorbed. And that's important because the ones examples that we're going to go through here a little bit will go on with biopharmaceutics. So let me just follow this, make sure you understand. So liberation means getting the drug out of the dosage form so that it can then be absorbed, go from wherever you put it, on the skin, in the stomach, up the butt, wherever you put the dosage form, it's got to get out of that dosage form, get across the mucous membranes and into the blood, okay? That's kind of the absorption phase. What does D stand for? Distribution. What does that mean? Well, the ibuprofen, my pain is in my head, so I don't need it to work in my stomach. It's got to get into the blood so the blood can circulate it to the brain or up into my head so that it can start to work there. That's distribution. Part of where the distribution goes, though, is to the liver. And what does the liver a big part of? The metabolism, right? The idea of M for metabolism is the breakdown, the chemical transformation of that drug into something that can then be eliminated, all right? All right, I think you kind of know that. Let's go on to biopharmaceutics, which is a narrower focus within pharmacokinetics, which is really, it talks about three things. It talks about the relationship of the drug as a chemical and how that relates to the dosage form. Remember my example for the tablet and to be able to release from the tablet. Or it could be a suppository, or it could be an injection. Think about you guys did your vaccine stuff, right? In your injections, when you inject it, how does that drug get out of the injection and from the muscle and into the blood? So it's the relationship between the drug as a chemical, the dosage form chemicals and how they interact with those, and lastly, where did you stick it, and where does it have to be absorbed from that location, and the chemical and how it does that. So it's kind of really the L and the A part as far as the overall pharmacokinetics. And lastly, because we are going to do some calculations on these, I want to make sure you understand within that idea of biopharmaceutics, part of it is bioavailability. It doesn't do you any good to put 100 milligrams of drug in the stomach when none of it gets absorbed, right? So what is the bioavailability? If that drug can't be absorbed from the stomach, if none of it gets into the blood, then you have to give it somewhere else. And that's why some drugs you can't take orally. You have to get via injection or something else because they're not bioavailable in that sense. Most drugs and chemicals have some varying degrees, but the amount of drug that comes out of the stomach and into the blood may be very different than the amount of drug that comes out of the muscle and into the blood when you give your IM shots. It may be very different than when you put it on the skin. So bioavailability is essentially relating the amount or the ability of the drug to go from where you put it into the blood, because for it to do anything for most drugs, it has to get into the blood. So let's just talk about that and define that. So we're going to deal with that last idea by defining a bioavailability factor. And we abbreviate that as a capital F, so a bioavailability factor F essentially is a fraction. And it is just this. It's the amount of drug that reaches the blood divided by the amount of drug that you dosed initially. When I gave that amount, then I'm going to compare it to the amount that finally made it to the blood. You know what the easiest bioavailability factor is to remember? IV drugs. Let's take a drug and I'm going to inject it directly into your vein. So I guess my question to you is, how much of that dose makes it into the blood? All of it. That's where you stuck it. You put it all in the blood. So the bioavailability factor for an IV drug is 100%. Everything you injected went right into the blood. There was no absorption. There was no other issues with it. So that's what I'm saying, is that the F value for an IV drug would be 1. But so the question is, what about if it's not? What if you take it orally? It probably isn't going to be 1. What will it be? And it will be different for different drugs by all means. Okay? So let's just finish with this example. If I give 40 milligrams of a drug and I give it by 3 different routes, one by IV, one by oral, and one by IM, how much drug actually makes it into the blood? For a 40 milligram dose, if I have different F values for this drug, let's just calculate how much makes it into the blood. And it should be pretty straightforward. When you do it IV and it's got an F value of 1, which essentially means 100%, that means all 40 milligrams make it into the blood. If the F value is 0.5, then what you're going to do is rearrange that formula and say that the dose that reaches the blood is equal to the F value times the dose that you gave. So all you got to do is take the F value times the dose you administered, and what's left is the amount that makes it to the blood. So if the F value is 0.5, then 40 milligrams times 0.5 is 20 milligrams. Similarly for the IM, if its F value is 0.9, 90% makes it into the blood, then take the dose, 40 milligrams times 0.9, and we said that 36 milligrams of that dose would actually make it into the blood. All right? Easy breezy, kind of? Now, the reason that this is kind of important, that's not really the way that we use this. So let me ask you this. This is a more important question. If I have been giving a drug 40 milligrams IV, and I now want to switch them to an oral form, what dose should I use? Can you answer that question? 40 milligrams IV would be what amount oral? What would you need to know? The bioavailability difference. How bioavailable is a drug, that same drug, when I give it orally? And I'm telling you the oral form of it is 0.5. That's its bioavailability. So give me the dose I should use for the oral form. Okay? That kind of reverses that question, and we'll do the same thing for the IM here. So how do you do it? You use the same formula, that is the dose that reaches the blood is equal to the dose you give times its bioavailability factor. But what's different now is we know the dose we want to reach the blood. We want 40 milligrams to be in the blood. So for the oral format, we're going to say that that 40 milligrams is equal to 0.5 times X. We don't know the dose, but we know we want 40 milligrams, and that only 0.5 of whatever the oral dose is is going to be what makes it. So we'll just divide the 40 milligrams by the F factor. So 40 divided by 0.5 tells us if we want 40 milligrams to make it in the blood, we have to give 80 milligrams orally by mouth. And if you look down there below for the IM form, if we want 40 milligrams to make it into the blood, then IM shot would have to have 44.4 milligrams. Does it make sense why you have to give more by that route? Because not all of it makes it into the blood. Okay, so this is typically how you would use the idea of these F factors to be able to calculate those. So let's do, and that just kind of shows you that. So let's do a question here. This may be a little more interesting to tie that same idea together here. It says, how many milliliters of a methotrexate injection containing a concentration of 50 milligrams per 2 mLs would be required or would be considered to be bioequivalent to a 15 milligram tablet? And it does come in a 15 milligram tablet. For whatever reason, we want to give that same amount of methotrexate by an injection. So wouldn't you just give 15 milligrams? Isn't there 15 milligrams of methotrexate in the tablet? So why don't we just give 15 milligrams of methotrexate from the injection? Because when we swallow that 15 milligram tablet, not all of that drug goes into the system. So that's why you can't just switch from the amount in the tablet to the amount from the injectable. We want to replace the same amount the patient would be exposed to by taking the 15 milligram tablet. So how are we going to do this? I've given you the F values, and the idea here with bioequivalence, we are saying is that we want the dose. The bioequivalence says that the actual dose that reaches the blood is the same from the 2 different dosage forms. To say that, we would say the F times its dose given would equal the F times the dose given. All right, so those two would need to be equal in the case of bioequivalence. So let's just set this up. And so we'll start off with the oral dose. And so the F for the oral dose we said was 0.4 in the question, times the dose of the tablet, which was 15 milligrams. So essentially the amount that's getting to the blood from the tablet is its dose, 15 milligrams, times its F value, 0.4. That we want to be equal to the amount we get from the IV, so, or in this case, the subcutaneous. So from the injectable, we would use its absorption, or its bioavailability factor of 0.8 times X. We're solving for the dose to use from the injectable format. Okay, but we know it's still only going to have an absorption of 0.8 as far as its factor goes. That's pretty straightforward math at that point. So 0.4 times 15 is equal to 6. Divide 6 by 0.8, and you get 7.5 milligrams. So it turns out, even though we're giving a 15 milligram dose, the only amount of methotrexate we need to replace is the amount from a subcutaneous injection that would be the same as 7.5 milligrams. That's not the end of this question, though, because it wanted to know the volume of the injectable to use. So let's just do one last step, and if I want 7.5 milligrams, then I multiply its concentration expressed as 2 mils over 50 milligrams, so that milligrams cancel. And again, that would calculate the volume of the injectable that I need to provide 7.5 milligrams, which is 0.3 milliliters. Any questions on that? I say this is an important slide. This is often the way you will see that F value used. And the take-home messages is the F value times its dose is essentially the amount that makes it into the blood. So if you want to go from one dosage form to another dosage form and to provide a bioequivalent dose, you set one equal to the other and solve for the dose usually to be able to give the right dose for the different route, depending on its bioavailability. All right? One more example. Let's see how you do on this one. This says a drug is 40% available by the oral route and 58% bioavailable by the transdermal route. Are you okay with the term transdermal? Across the skin. All right? If a patient is taking a 2.5 milligram oral capsule twice a day and is switched to a 2% weight per weight nitroglycerin ointment, how many grams of the ointment should be administered as a single daily dose to provide the same bioequivalent dose to what they had been getting through their oral capsules? So we want to take the amount of nitroglycerin they've been getting orally and find out how much of this ointment to use to provide the same bioequivalent dose. So where would you start? Well, we're trying to replace the oral version, right? So let's start by determining what was the total amount of nitroglycerin I was getting from my oral dosing. I said they were 2.5 milligram capsules, and this is always a trick like would be on the test, but how many are they getting per day? 2, twice a day, right? So that's 2.5 milligrams per capsule, but they're taking 2 a day. The total daily amount of nitroglycerin is 5 milligrams. That's the amount they're getting per day. That's the amount of nitroglycerin that we're going to need to provide using our ointment, okay? Well, we just want a bioequivalent dose. So let's take the F times the dose on one equal the F times the dose on the other. So if we start over here with the oral format, we were given that essentially oral route is 40% bioavailability, okay? The F is simply expressed as a fraction, not as a percent. So what is 40% is 40 divided by 100. What does that equal to? 0.4, right? So the F would be 0.4 for the oral. We were told the daily dose was 5 milligrams, so 0.4 times 5 milligrams on one side should be equal to the F for the transdermal route, which we said was 58%. That's, well, 58 divided by 100, that's 0.58. So the F is 0.58 times X. I'm solving for the dose. I want the dose that would be equivalent to the oral. Sorry for hitting my mic. So 0.4 times 5 is 2, and divide 2 divided by 0.58, and we found out that the amount that we need of nitroglycerin purely from the transdermal route is 3.44. So I need 3.44 milligrams from my transdermal ointment. However, what's the last step? To actually determine the amount of ointment, because the ointment isn't pure nitroglycerin. Remember we said it's a 2% weight per weight. So the last step would be to take my 3.44 milligrams. I converted it first to grams, so don't freak out, but so converting milligrams to grams by dividing by 1,000, okay? Then multiplying it by the concentration expressed as 100 grams of ointment over 2 grams of nitroglycerin, so that my grams of nitroglycerin cancel, and my final value would be in grams of ointment. So essentially this says I would need 0.17 grams of ointment to provide the required amount of nitroglycerin to be absorbed topically. That would have been the same had I swallowed 2 essentially of those 2.5 milligram capsules. It's kind of cool, right? And you see a little bit of the, anyways, I love pharmacokinetics. It's got some important applications to be able to do these things. You'll still learn a lot more about all of this, but it's kind of an interesting idea here. All right. Now, you can't do pharmacokinetics without talking about a plasma drug concentration versus time curve. All right, so I've got to do this. We kind of talked about this way in like the first lecture type of thing, but now that you know more, if you've had some pharmacology, so if I said duration of action, I'll just tell you now, how long will this drug work? How would you know? Looking on this graph, could you tell me what the duration of action is? Well, can anyone answer that? And then I'll maybe go on quickly. I might not, but I would, maybe. Okay, here, the answer to that question is right here. This to this, all right? So if you understand how to use these curves, they kind of make sense. So let's make sure you know what you're looking at. A plasma drug concentration. What is on the the x-axis? X-axis is time. Now, I didn't give you units for time. It could be minutes or hours or something else, but it is time. So on 0, 0, starting the far left at the very bottom, 0 on time is 0, and then it's going out extending in time, over time. What are we going on the y-axis? On the y-axis is the concentration. It's how much drug made it into the blood. Remember, this whole thing, for a drug to produce any effect, it has to get into the blood. So, again, the higher the level on the y-axis, the higher the concentration is. All right? So what is really important and what we're looking at in terms of this is this dark line. So the line that's going up and coming down, this is actually what's being measured. It's the amount of drug left in the blood. Okay? Now, let me ask you this. Looking at that curve, was the drug, in this example, given orally or intravenously? Come on. You guys bothered to show up, so give me an answer here. Any ideas? I would argue this. What would the concentration be in the blood? If I injected it, boom, into the blood, what would the concentration of the drug be? High. Would you agree? It would have started up here and gone down like that. What you're seeing here, the fact that you're starting from 0 and you see this increase, it's a rapid increase, but it starts at 0, 0, and it goes up to this peak level. What phase of that? That is, what you're seeing is absorption. You're seeing the drug being released from inside the stomach, for example, and getting into the blood. And it gets more and more and more and more and more and more and more. Why does it peak? Because at some point there's no more drug to absorb. Would you agree? Then how come, let me ask you this, after we've absorbed it all, how come it just doesn't stay forever up there? Once you take a drug into your blood, does it just stay there forever, or does the body get rid of it? It gets rid of it. It starts to eliminate it. It starts to become metabolized and excreted, whether it's through the GI tract or through the kidneys, wherever it is, the drug is gotten rid of. That's why once you finish absorbing it, it starts to go back down in the elimination phase. So do you see where it says elimination phase? At what point will the absorption be exactly the same as the elimination? The maximum. So if you look at the Cmax there, the peak of that curve, that has a special value. We call that essentially Cmax. Cmax meaning the concentration maximum that the drug ever reaches. It reaches Cmax at Tmax. So if you look on the time at the bottom there, we call Tmax a special time. That's just the time that you get Cmax. All right, so you can kind of see that listed on there. And that's the point at which absorption is now equaling elimination. Because after that point, which one takes over? Elimination, because it starts to go back down. So just to kind of help you have absorption to begin with, and then it tends to peak when absorption now just equals elimination. From there on out, it's going to be elimination that takes over, and that's why the plasma concentration starts to go down. Okay, so got the shape of the curve down, I hope. These are really important ideas too. What does MEC stand for and MTC stand for? MEC is minimal effective concentration. Let me ask you this. Have you ever taken an ibuprofen for a headache? Does it work like right away? No, why not? It has to be absorbed. It has to reach a certain threshold blood level. It doesn't have to be at its peak, but it has to have enough drug in the blood to be able to get to where it needs to go to produce its effect. So MEC stands for a minimal effective concentration. So for this drug, remember I said about kind of this duration of action? It won't start to work until the levels get to this minimum effective concentration. How long will it work? It will continue to work as long as the concentration is what? Above the minimal effective concentration. So you'll notice when it starts to fall back down under elimination, it hits that minimum effective. So the time from here to here is the duration of action. Hopefully that kind of makes some sense. Okay? So do we want our Cmax to be above our minimum effective? Yes. Do we want it super high? Maybe. What we don't want it is to exceed what? We don't want this point here to be higher than that point, because what does that concentration represent? The minimal toxic concentration. Would you agree too much of a good thing is a bad thing? So you get too much drug in there, instead of getting your beneficial effects, you start to get side effects. You get bad things that start to happen. So what we would like is we would like our peak to occur well within above the minimum effective, but below the minimum toxic. So again, we're getting our effects, but not getting any side effects. So that's why that difference between that is important, okay? How do we describe that difference? Would it be good for a drug to have should these two lines, the minimum effective and the minimum toxic, should they be close together or should they be separated quite a bit? The further apart they are, then the safer the drug is. You can get well above the minimum effective and yet be nowhere near the minimal toxic. What do we call the difference between those two? The range between the minimum effective and the minimum toxic is called what? The therapeutic range. Have you guys talked about that term or kind of familiar with that term, the range? Are there some drugs that really have a narrow range? The narrower that range, the more potentially toxic and dangerous that drug is, or hard to dose. Those are drugs, I'll give you a hint, those are drugs that have a lot of dosage forms, a lot of strengths. For example, can you think of Synthroid? Have you ever dispensed Synthroid or levothyroxine? What are the strengths they come in? Like in their micrograms, right? 0.1, 0.125, 0.117. There's a lot of these little strengths because the range for that is so sensitive, you can easily go too high versus too low. So just an example of doing that. And the last thing I'll say here, because I know we're only getting done, we hadn't talked about this, AUC. What does AUC stand for? Anyone tell me what that abbreviation is? Area under the curve. So would you agree that some drugs may peak higher than others, but some drugs may last longer or be slower to be eliminated? Okay, essentially, if you look at the area under the curve, regardless of the exact shape of that curve, the larger the area under the curve, the larger the gray amount of area there, the more what? The more that body was exposed to that drug, that longer that drug was in the body to produce some effect, okay? So you can use the area under the curve, and this is what you'll do in pharmacokinetics. That's one of the things you'll calculate is the area under the curve. It doesn't tell you whether the peaks were too high or too low. It won't tell you exactly how long it worked, but it can tell you overall how long that body was exposed to that drug. And again, the larger the area under the curve, the larger the drug was there to be able to produce an effect. A small area under the curve is a drug that is eliminated rapidly or doesn't absorb very much. It didn't have much effect on the body if it has a very small area under the curve. Okay, so those are just some important kind of topics under that. And then second main thing, we had been talking about absorption a little bit and how the drug gets into the system. Now let's talk about distribution, because once the drug gets into the blood, where does it float around? It floats in the blood. It can either float around unmolested by itself or it can be bound up by proteins. And again, a lot of drugs are actually bound by proteins like albumin. The reason that's important, and that's kind of important on this picture here, I try to illustrate in this area kind of up here, that it's really only the drug that's unbound, that's free, that can do whatever it wants to do. Kind of like you guys in class, right? You want to leave? You can leave. I don't bind you to your seat, right? So the idea here is a drug, though, that's unbound is the only drug that can leave the blood and go into the tissues and produce an effect. So would you agree? A drug that's highly bound by plasma proteins, let's say it's 90% plasma protein bound, there's not much drug left to do anything. The lower the protein binding, that doesn't mean a drug is more effective, but at least it can leave the blood to do something somewhere else. So clearly being able to calculate the relative amount between the total amount in the blood versus the amount bound to proteins versus the amount that's therefore what's left over is unbound. So the abbreviations on here is the concentration total means the total amount of drug. And think of it as a percentage, like 100%. The total percent is going to be either the amount that's bound or unbound. It's easy, one or the other. So this is not a difficult concept, and the calculations are kind of a joke, but it's important to understand the idea here. And this alpha is simply determining the fraction, and the fraction is unbound to total. Because what we really care about is of the total amount in the blood, how much is unbound, because that's the percent that's going to be available to produce an effect. So essentially, some definitions there, total is bound plus unbound. The alpha is the ratio, though, of the unbound to the total, which also means then the unbound to the combination of bound and unbound. All right, so some simple calculation questions I have that is if the alpha of a drug value for a drug is 1/3 bound to protein. Okay, what is the alpha? If 1/3 of the concentration is bound to protein, what is the alpha for this drug? Well, remember, what we care about is the unbound, and we were told that 1/3 is bound. So I know it's just very intuitive to this, but let's just set up the formula that the total, CT or the total, would be equal to bound plus the unbound. We were told that 1/3 of a fraction is bound, and if the total is 1, or 100%, then what is 1 minus 1/3? 2/3. So clearly 2/3 of the amount would be unbound if 1/3 is bound. The alpha is simply the ratio of the unbound to the total. So if 2/3 is unbound over 1 total, then the alpha is 2/3, which you would then probably express as a percent, meaning 67. 0.67 is the actual alpha is 0.67. But that essentially means 67% of the amount of drug in the blood is unbound. Okay? Easy enough concept to understand. It's really not a calculations thing, but it is an important factor in pharmacokinetics. If you want to look at drug effect, you have to consider how much is bound versus unbound, because it's only the unbound that's going to do anything. This is a much more important concept in, I won't say difficult math, but this formula of VD equals D divided by CP. This little thing right here, this is important. You got to know this. You will see this all the time in pharmacokinetics. It's a core idea, and it's the definition of a volume of distribution, VD. Okay, make your jokes all you want on that, but in this case, it means volume of distribution, all right? And it's a key idea, because now the idea is, let's say, here's the deal. Let's say I inject 100 milligrams of drug directly into your vein. It's an IV. Don't worry about the absorption and oral thing. If I give you a drug IV, boom, all 100 milligrams of that drug goes straight into the vein. Where does it go? Does it stay in the blood? Whether it's bound or unbound, that whole discussion we had, that still relates to the amount of drug where? In the blood. We're now going beyond the blood. The question is, when you inject drug into the blood, does it stay in the blood or does it go anywhere else? To produce an effect, what did we say the drug has to do? Go somewhere else. So what the volume of distribution does is it's a fictitious volume. It's not a real compartment in your body, and that's why students don't like this. It's kind of a theoretical thing, because we don't know where the drug is going. What the VD does is it compares the dose that you gave and the plasma concentration that you got from that dose. The difference between those two, not like a subtraction difference, but if using that formula, the difference between those essentially describes the volume in liters or milliliters. It's a volume that appears that drug seemed to go into. The larger the volume, the more the drug left the blood. That is, if it looks like a huge volume, maybe it's like 50 liters. That's a ginormous volume. Sorry. That doesn't mean there's 50 a liter volume of you somewhere in your body. It just means the difference between what you started with your dose and the plasma concentration that you measured. The difference appears to be that drug dispersed in a volume of 50 liters. If it disperses in a volume of 0.5 liters, is that much smaller? That means it didn't hardly go anywhere. The little bitty space that it left the blood was a really small space, meaning it didn't really leave the blood very much at all. Most of the drug is still in the blood. The larger this VD, the larger this apparent fictitious volume, the bigger the difference is between the dose I gave in the blood and what remained in the blood. Because the more that it leaves, the larger that apparent volume is. Hopefully that explains it a little bit. You'll keep learning this in pharmacokinetics. I think what's important here a little bit to understand in terms of why is this important, well, drugs have different volume of distribution. They very well do. Again, the greater ability to leave the blood are drugs that are not polar, that are lipid soluble, that don't ionize. If you think about those, charged particles can't cross through membranes very well. They can't leave the blood very well. So drugs with high VDs are the opposite of those. Drugs with low volumes of distributions are the ones that do ionize. And when we talked a little bit about pKa and some of those things before, those drugs that ionize and become electrolytes, they can't leave compartments very easily, and therefore you tend to see them have a very low volume of distribution. Okay? Why is this even important? To produce an effect, what did we say the drug has to do? It has to leave the blood. So once again, it's a measure of using pharmacokinetics to determine partially why a drug might be working or may not be working. If it can't leave the blood, then it can't do anything. Okay? In the end, the formula that you got to know and the terms that you got to be able to use, if I give you this formula on a quiz or something on the test, it's that VD, the volume of distribution, is equal to the dose over the plasma concentration. Okay? So let's answer one of those questions. So this is what something might look like. It would say, a patient received an intravenous dose of 10 milligrams of a drug. A blood sample was taken, and the concentration of that drug in the blood was measured to be 40 micrograms per 100 milliliters. Calculate the apparent volume of distribution, okay, in liters. So I will point this thing out here. Here's some things we got to point. The only trick to these calculations, because it's VD equals dose over CP. I know you guys could do that. That's not hard, but be careful, because liters aren't what? Milliliters, and milligrams aren't micrograms. So before you actually do the math, you've got to make sure your units match and that they cancel each other. In one sense, milligrams and micrograms are going to have to cancel each other one way or the other. And again, our final answer has to be in liters, not milliliters. So how would I start with this? I would set up and do one of my things at a time, because I know VD is dose divided by concentration. So let me just say dose. Dose equals 10 milligrams, right? Are you okay? Do you see where that came from? 10 milligrams, all right? So that's fine. I don't need to change that. I like milligrams. So let's look at the concentration. So again, maybe I should do this here. The 10 milligram dose comes from right there. This is, though, the concentration we were given. My problem is that milligrams don't match micrograms and milliliters don't match the liters. So what I chose to do, and you could have gone, I could have changed the dose from milligrams to micrograms, but in this example, I'm changing the units of the concentration. I'm not changing the concentration, but I'm going to re-express my 40 micrograms per 100 milliliters in the units of milligrams per liter. All right, that way milligrams match milligrams and liters match the units that my answer needs to be in. So all I'm doing is rearranging that. So let's convert that. I started with the weight first, so 40 micrograms I multiplied by 1 milligram for every 1,000 micrograms so that micrograms cancel. I'm now in milligrams. That was easy. Now let's get rid of milliliters, and that's because there's 1,000 milliliters per liters, so that will cancel those units, and my final units are in milligrams per liter. So if I do that, all I'm doing is re-expressing my plasma concentration, the same number, but in different units, is 0.4 milligrams per liter. So far, so good. All we did was change units on that. Now I'll use my formula. VD equals dose divided by CP. When I put my dose, 10 milligrams, and divide it by my re-expressed concentration of 0.4 milligrams per liter, you see where milligrams will now cancel, and liters will come out of the bottom and be on top, and be essentially the math. 10 divided by 0.4 is 25 liters. Okay? Any questions on that? So I will still say, if I give you one of these questions, the math would be pretty straightforward. It just double check the units, because I can give you dose in any sort of micrograms, milligrams, nanograms. Concentrations can be expressed in different units. So double check your units. Before you divide something, make sure units cancel. That's the only trick to that. All right? All right. This last topic here is, no one likes this. Here's the thing. Once this light bulb comes on, you will thank me. It probably won't happen today. I apologize for that. But once you finally understand what a first order reaction is from a zero order reaction, from a second order reaction, your life will be much better, because next semester you have a solutions and solubility course taught by pharmaceutical chemistry, which includes a big section on drug degradation and how about drugs degrade over time. Some degrade by a zero order, some by a first order, some by a second order, okay? I'm going to talk about the same idea of first order reactions in the terms of pharmacokinetics, but this is a bigger understanding that needs to be applied to different topics, so hopefully this will get you started. So here's the deal. Let's just say I gave you 100 milligrams of drug into your blood, okay? And it will be removed by the body. Okay? If it is removed by the body, so here's the deal. Here's the dose. Here's the drug concentration. When I gave you that 100 milligram dose, boom, I measured it immediately, which is not even possible. Let's just say when I give you that dose, that's the first concentration immediately when I gave you that dose. Again, there's no absorption. I gave it IV. So the drug levels, how come the drug levels don't just stay like this the entire time? What does the body do to the drug? Removes it, right? It eliminates it. So the drug levels are going to go down. Why doesn't drug levels in the body go down like this, where instead this is what it actually does? So this is the real thing. The curve shows you what really happens over time. How come it doesn't just fall straight down? And again, the reason it makes a big difference you're going to see here in a little bit, because it doesn't. If it fell down in a linear fashion, that means the body removes the same amount of drug constantly over time. Every second it removes the same amount, because the slope, we're going to have to talk about the slope of that line, doesn't change. It's a straight line. The slope on the top is the same as the slope on the bottom. The rate of degradation or removal from the body is the same over time. That is easy. You can calculate a slope and you're done. But in the body, that's not the case. What is happening here, and this is, again, this text does a good job of trying to explain it here. I'm sorry for all my lines there. Is that when the body starts to, give that 100 drugs, there's a lot of drug in the blood, the body removes it more quickly. It's concentration dependent. And the answer, with a first order reaction, the rate of the removal or the elimination, the change in the concentration over time, is concentration dependent. Which means at the beginning, when you have all of that 100 milligrams of drug over there, the rate of elimination is faster because there's a high concentration. That's why if you look at the slope here, it's pretty steep. But why is the slope over here way further down? Because as you lose more drug, then the rate also decreases. When there's less drug, then the rate of its own elimination decreases. So that when you get down to very small concentrations of the drug left, that's why it just doesn't go to zero. It hangs around in very small amounts over a long period of time because it doesn't have much concentration to drive the elimination. So in the end, the higher the concentration, the higher the removal. That's why it's a sloped curve, very steep curve at first, but it levels out as the concentration lowers, so does its own rate of elimination. It affects its own rate of elimination. How would you describe that reaction? That's called a first order reaction. All a first order reaction means is that the rate it removes itself is dependent on its own concentration. Therefore, the rate changes constantly as the concentration changes constantly. They're dependent on each other, which makes it a much more complicated thing to deal with. Okay? The reason this is important in pharmacokinetics, let me just show you this. This is kind of a big formula. You use this formula all the time right here. So a little bit of derivation from that. What that formula says, I'll start with that. CT stands for some plasma concentration at some time after the dose. So I give you 100 milligrams IV. What will the plasma concentration be in 2 hours? Might that be important? Because sometimes you need to know when to give another dose. So would you agree it would be nice to be able to predict the plasma concentration after giving a certain dose of the drug? Well, this allows you to do it because the concentration T says at the 4 hours or whatever time you're interested in, that plasma concentration will be equal to the C0, which is the initial plasma concentration. C0 stands for the concentration at time 0. That's the very highest, the initial plasma concentration. It's that concentration times, and again, E, this is the E from the natural log idea, so E raised to a minus KT. All right, so really the 1 CT is equal to the C0 times some factor. So would you agree we need to spend some time thinking about this because that's the factor that's going to affect how my plasma concentration changes? Well, that's kind of comes from over here, if you will. That's why I kind of went backwards. Because the rate of change in concentration, the dC dt, the rate of concentration change over the time is equal to, and again, the value is negative because are the values over time going down or are they going up? They're going down, right? We're removing the drug. We're eliminating. So the concentrations are going down. They're getting smaller. So that's why there's a negative sign. K just stands for this magic constant. It's a constant. It's going to be different for every drug. It's what's unique about the way the body handles that drug, but it's a constant for that drug. Regardless of how much drug you have, the body handles it the same way, okay? Times its concentration, though, because we do say it handles it the same way, but dependent on how much drug is there. So that's why you multiply by the concentration. That's what makes it difficult, all right? So the minus K is the minus K in that important formula there, all right? So having said that, part of what you're going to have to do in pharmacokinetics is basically measure drug plasma concentrations over time, plot them in graphs so that you can determine K. Once you know K, you can do a lot of calculations, but you need to know the K value, all right? So a lot of what we're going to talk about, and I'll come back to these formulas. These formulas are all the same formula, just rewritten. So one thing I will warn you now going into your next semester with pharmacokinetics and with the drug solutions and solubility, when you deal with first order reactions, you got to know logarithms. You need to be comfortable with both natural log. And how do you abbreviate natural log? ln, right? So on this formula, they say ln. Is there a different log? Don't make bathroom jokes. A different log, log, right? Log base 10. It's the same thing, but in a different factor, using a different value, a 10-base system instead of the natural base system, all right? So both of those are used interchangeable in pharmacokinetics. You're going to see that here in a minute. We're going to go from natural log to log base 10. So some of you are a little sketchy on some of your log functions. So for example, what is the log of A times B? Log of A plus the log of B. So going back to a little bit of math stuff, there are some fundamental rearranging formulas with logarithms that you're going to need to do, not for this class or the final, but going forward. That's what I'm trying to illustrate, is that's why some of this math gets more difficult. And all this slide was trying to illustrate what I said before. You need that function because it's not a zero order where it's just the K. It's the first order has both K and C. And that makes it a logarithmic function, and it means that you get that curve when you plot it. All right? So how can we determine K? Here's the deal. I told you here, we got to get K. That's what we got to get K. If I had a straight line, K is equal to the slope. If I had a straight line, all I would have to do is determine the slope, and that slope is equal to k. So in a zero order reaction, all you got to do with a straight line, measure the slope, that equals k. But in a first order reaction, what do we need to do? We need to convert our curve into a straight line. We can't deal with the curve. When I plot concentration versus time, I get a curved line. So what can I do? Well, don't plot the concentration. What can you plot? The natural log of the concentration. Remember how we said it's a logarithmic function in a first order reaction. So instead of just saying concentration versus time, if I take whatever concentration I want to plot, take the natural log of it, and then plot natural log of concentration against time, look what happens to the curve. It turns out to be straight. I love that, because what can you measure on a straight line? Slope. And once you measure that slope, you can say that slope is equal to minus k. It's minus because it's going down, but that k value is going to equal the slope of a graph when you plot the natural log of c versus time. Isn't that easy? Kind of easy, kind of confusing, kind of easy. The trick is you've got to manipulate the data in terms of the graph. You've got to take your real data and know that it's first order, and therefore I have to re-express it using logarithms to be able to generate a straight line. Okay? But when I do, then bingo, I can measure my slope. All right? So that's pretty cool. Now, let's just talk about one other really important idea in pharmacokinetics, and it's half-life. All right? So, half-life. What is half-life? Half-life is the time. It's a time. Half-life. Time that it takes for the concentration to fall by what? 50%. A half-life is the time. In minutes, hours, you can express it in whatever units you want, but it's the time. Half-life is a time, but we know what's special about that time. It's the time that it takes from one concentration to fall to what? Half of that concentration, to 50% of that. That's why you'll notice, this is an important idea, a half-life, this proportion of whatever the concentration you're looking at over the initial where you started at, it's for half-life, that amount of time is always going to be 0.5 because it's the time it takes for that concentration to fall by 50%. All right? Well, if we know that, we can actually put that 0.5 back into that same formula I showed you on the previous page and take the natural log of 0.5. Okay? If I take the natural log of 0.5, you do that on your calculator, it's negative 0.63. So this number here is simply just the value of the natural log of 0.5. All right? Well, if we set that equal to, and going back to this formula, so this number now is equal to that, essentially you can say that T1/2, or the half-life, is equal to 0.693 divided by K. Why is that important? What do we need to solve for a lot of the times? K. Now, if we can find the half-life, can we find K? Yes. Okay? And we can find half-life using our graphs. And that's why using graphs in you're going to be graphing all the time in pharmacokinetics, because you graph the data, and based off of how you graph the data, you can get things like half-life on there, you can get C0 or CB0s, and then use them in these formulas, such as the formula for half-life. In the end, if you want to know nothing else, make sure you kind of know this. Okay? That is the formula for half-life. Okay? And you're going to see that here in a minute. By using that formula, we can go back and find these kind of relationships. So let me illustrate that to you. So here's the question. It says, if the half-life of a drug is 4 hours, what percentage of the drug administered would remain in the body after 15 hours after administration? Okay? So the half-life of a drug is 4 hours. I want to know what percentage, what fraction of that drug amount is remaining after 15 hours after administration. Now, wait a minute. If the half-life is 4 hours, then 4 hours I would have half of what I started, right? Wouldn't I be totally gone by 8 hours? If I lose half in 4 hours, wouldn't I lose the other half in 4 hours? No, that's the trick. I would if it was a zero-order reaction. If the slope of the line was constant and not dependent on concentration, yes, that would be the case. But not in a first order. Remember, it is concentration dependent. So the rate at which I lose drugs are going to slow over time. So what I lose after 4 hours is half of what I had at 4 hours. And after, and so forth. So okay, we'll go through this question. So how do you solve this question? Well, what we can do, remember, now that we know a half-life, do we have a formula for half-life? We did. We just had that formula for half-life. So let's use that formula, which was this formula right here. Remember how I said what's very useful is you being able to solve for K, because K is the answer to a lot of these questions. So let's find K. Let's use the half-life equals 0.693 divided by K. I don't know K, but what was I given in the question? I was given the what? Half-life, so I can just rearrange that and say, okay, if T1 half equals 0.693 divided by K, well then K equals 0.693 divided by T1 half. I was told the half-life was 4 hours, so K is equal to 0.693 divided by 4 is 0.173 reciprocal hours. And again, you have to be careful with your units here a little bit because I could have given you half-life in minutes or anything else. So again, the half-life can be expressed in different units. In this case, in this question, my K value is now 0.173 reciprocal hours. Now, what was the point of that? Well, remember that formula that I said related CT to C0, which is essentially the concentration of my time compared to what I had. It's the amount remaining. The log of that is equal to minus KT. Well, now guess what? I have my K. I can put my K into this, okay? And I can solve. What I'm solving for is this, all right? I want to know, well, no, I'm not solving for that. I'm given that. So 15 hours is my T value. So I know 15 hours. I have a time that I'm interested in. I want to know what essentially the amount of the concentration is. So if I essentially solve for that, so if I put these Ks and my Ts in here, there's my K value, there's my T value. I shouldn't have covered it up, sorry. Pen. And then essentially E raised to the negative 0.173 times 15 hours, that essentially to the negative KT. You do that math, and you need to be careful with your calculators. This is a good chance to practice your logarithm functions where you do e to the x on there. But essentially E raised to a negative 2.6 is 0.074. That's essentially the fractional value. If we want to express it as a percent, multiply that by 100, that would be 7.4%. So what we did is what we have just said, that essentially if a drug has a half-life of 4 hours, then after 15 hours, which is going to be multiple iterations of the half-life, but after 15 hours, how much of my initial dose is left? 7.4%. And that's kind of cool that you can predict that. For this drug, we know that, again, after 15 hours, I'd only have 7.4% of what I started with. Okay? All right, so in the end, these are the formulas that we've kind of been looking at before, rearranged. And I say rearranged in the sense that you're going to see why here in a minute, why sometimes we will take these logarithmic functions and take the natural log formulas and convert them into log base 10 formulas. And so the formula on the left of this slide shows you the natural base, but what you'll do a lot of the time is use it in a log base 10. And to convert from natural log to log base 10, you have to essentially divide by 2.303. So that's where that number comes from. You'll see that here quite a bit. And essentially when we go from natural log to log base 10, that's why we divide by 2.303. That's the difference between those two functions. All right? Last topic really on this idea is this idea of graphing. Okay? And let me just, because it starts really with this. This is where, and again, you won't get, I'm telling you on the final exam, I'm not going to give you a list of these plasma concentrations and have you graph them out. That's a little bit too far in advance. That's what you will do in your pharmacokinetics class. But let's just see if you can understand and be able to do some of this math. You get those values, you need to plot them. But the idea here is to solve for K, we need a straight line. So if I were just to plot them like I did with just concentration against time as we described, I get a curved value where I cannot determine the slope, so I could not calculate my K value. So what we said is plot natural log of concentration versus time. It gives you a straight line. Okay? And there's the formula. From that, if you solve for K, then you can determine any concentration as it relates to where it started from at any point in time where T is afterwards. If now the slope of this line is equal to a 9 minus K, all you have to do is calculate that. Here's the deal. A lot of times you need C0. What does C0 stand for? Plasma concentration at time 0. If I inject a drug, 100 milligrams IV, can I measure it at the same exact time I give it? No, because it hasn't even had time to distribute through the body yet. So normally you can never measure C0 directly. In this case, the first time point I could measure, you look at this value here, I try to do this, let me erase that and use a different color. Okay, so again, there's the first plasma concentration I could measure. And it was basically at time 1 hour. But I need my C0. What can I do? What you'll do is, see how by plotting it here you get a straight line? Well, you can just back extrapolate. And where it crosses the y-axis, which would be kind of over here, that's going to be your C0. So you can still, from a graph, you can determine your C0, you can measure the slope and get the K value. All right? That's one way of doing it. Another way you could do it is, instead of plotting natural log of K, you plot log base 10 of CT versus time. So log base 10 of the concentration instead of the natural log of the concentration. If you do that, then the only thing that changes is the fact that your slope is not minus K, your slope is minus K divided by 2.303, because that's the difference between natural log and log base 10. And you're thinking, I don't care, this is stupid. Here's the deal, a long wind up for this. This is what you will do in class with pharmacokinetics. You're going to get semi-log paper. And make sure you understand that term. What does semi-log paper mean? It means that the y-axis is scaled on a log base 10 scale. The x-axis is normal linear. That's why they call it semi-log. Semi meaning the x-axis is linear, but it's the y-axis is logarithmic, base 10. And so what you'll see is the graph, and I know it's hard to kind of see on here, but it's done in cycles. There are darker lines, heavier lines, and lighter lines. And each cycle on a logarithmic paper is a factor of 10. Okay, it never starts at 0. You always add what you normally think of 0, 0, and it's 0 on the x-axis because it's linear, but right here on the y-axis, it's not 0. You pick what you want it to be. So in this case, bear with me on this, I put my lowest value on here to be 0.01. Okay, and then there are 10 little lines between that cycle and the one above, 1, 2, 3, and I won't get this right, but there are 10 little lines. So from 0.01, the next line up is 0.02. 0.03, 0.04, 0.05, 0.06, 0.09, and then I'm at 1. After 0.9 is 0.1. But guess what? The next little line is not 0.11, it's 0.2, 0.3, 0.4, 0.5, up to 1. And then each little line from here is 2, 3, 4, 5, all the way up to 10. So the point being is, do you see where every cycle here is a 10-fold increase? From one cycle to the next, it increases 10-fold, okay? And it's not the same. Each little line is worth a very different amount in each cycle of the paper. So it's going up exponentially fast if you think about the y-scaling. The advantage to using and actually plotting your real data on that y-axis is it will account. It basically logs the value for you, because in terms of its positioning, it will position each point relative to each other in a logarithmic fashion, since the lines are not worth all the same all the way through the paper. Okay, no one's lost with that. In the end, if you do use a semi-log paper, then you don't have to change your data, you just graph it. Whatever your concentration is, that's the concentration you use. As long as you're using the semi-log paper, the logarithmic scale will put the point in the right place without having to take the log of it. Then you can just determine the slope, and again, the slope is essentially going to be minus K divided by 2.303, because again, it's still a log base 10 factor. So in the end, I knew nobody would like that, but this is where you're going in pharmacokinetics. Graphing skills are going to be important. Understanding logarithms are going to certainly be important, okay? To finish up here, because these are kind of some silly questions at the end that I inherited this, but let's just, because this is kind of the questions you might see on the quiz, if you would, in terms of this course. So let's answer this. It says in normal subjects, blood makes up about 7% of body weight, okay? 7% body weight. I know we said blood, but we're talking about weight. So that 7% is what? It's a weight per weight. There's 7 grams of blood for every 100 grams of body weight. That's what that 7% means. Calculate the approximately blood volume in liters for a man weighing 70 kilograms. All right? So how would we set that up? Well, my weight, 7%, is in grams. So let's convert 70 kilograms, first of all, to grams by multiplying by 1,000. That will cancel kilograms, so I'm now in grams. Then I can take my 1,000 grams of essentially body weight and multiply it by that 7%, where again, 7 grams of blood per 100 grams of body. Well, my grams of body weight will cancel, and that gives me grams of just weight of blood. I didn't want the weight of the blood, I wanted the volume of the blood. So again, if we make an assumption that the specific gravity of blood is about the same as water, then we'd say about 1 gram per mil. So if I multiply it by that specific gravity setup where grams cancel, and I'm in milliliters, then simply to convert it, the final answer needed to be in liters. So let's multiply by, in 1 liter, there's 1,000 milliliters. So that milliliters cancel, my final units would be liters. And you do that math of going all the way across, and you'd get 4.9 liters. You didn't know you had that much in you, did you? Anyways, hopefully it stays in there. All right, the reason we asked that question was, that tells you about on average how much most people have volume of blood in them. That's kind of important because you can use it down below. It says, if the drug Zantac reached peak blood levels of 500 nanograms per mil. So we gave a dose, and the peak drug level was 500 nanograms per mil, 2 to 3 after taking an oral dose. Calculate the total amount of drug that we gave. All right, so I know a blood level, but I don't know my dose. I'm solving for dose in this sense, okay? What dose did I give to get a blood concentration of 500 nanograms per milliliter? To do that, we've got to use, in this case, this answer here. So we're going to carry that answer down and say, okay, if we assume that a patient has about that volume of blood, so if we start with the fact that they're going to have 4.9 liters of blood, let's first convert that to milliliters, okay? So I'll cancel that by multiplying by 1,000. Then I can multiply by that concentration. I was given this concentration here, so let's multiply by that. If I do that, then milliliters will cancel, and I'll know my dose, but it'll be in nanograms. And again, the question wanted to know milligrams. And again, you can do this in one jump, but it's too much for my brain, so I know there's 1,000 nanograms per microgram. I know that's a really bitty number. So 1,000 nanograms per microgram. Then I can go from micrograms to milligrams because I know there's 1,000 micrograms per milligram. So if I do that and multiply that across, then again, my final units will be in milligram, and that's where I got the 2.45.